sklearnexceptionsFitFailedWarning. Description: the fit-failed warning is a warning issued by scikit-learn when a model fails to fit the training data properly. This often happens when the model encounters issues like perfect collinearity in features, a lack of convergence during optimization, or insufficient data inputs. Training data: this is the dataset used to train the machine learning model. It typically includes features-independent variables and target labels-dependent variables. Model: this refers to the specific machine learning algorithm chosen for the task. Examples include linear regression, decision trees, support vector machines, etc. Outputs: fit-failed warning. This warning is emitted by the scikit-learn model's fit method. It informs the user that the model has encountered difficulties during the fitting process. Model object: even with a warning, the model object might be fitted, but its performance might be unreliable. Steps: the model is initialized with chosen parameters. The model's fit method is called, attempting to learn patterns from the training data. If the model fails to converge, fit properly, or encounters issues, the fit-failed warning is triggered. Metrics: training score. This metric assesses the model's performance on the training data. It can be helpful to identify potential overfitting if the training score is significantly higher than the validation score. Validation score: this metric evaluates the model's performance on a separate dataset, typically called the validation set, which is not used for training. It helps gauge how well the model generalizes to unseen data. Visualization plots. Residual plots: these plots show the difference between the actual target values and the model's predictions. They can reveal patterns in the model's errors and suggest potential issues. Feature importance plots: these plots highlight the relative importance of different features in the model's decision-making process. They can help identify features that are contributing most to the model's performance. Fine-tune parameters. Regularization parameters: these parameters help prevent overfitting by adding penalties to the model's complexity. Examples include L1, L2, and elastic net regularization. Learning rate: this parameter controls the step size during optimization. A smaller learning rate can lead to slower convergence but may improve stability. Number of iterations: this parameter specifies the maximum number of optimization steps allowed. Increasing the number of iterations might improve convergence but can also lead to longer training times. Uncertainty methods. Confidence intervals: these provide a range of values within which the true prediction is likely to fall, considering the model's uncertainty. Bayesian methods: these approaches incorporate prior knowledge and uncertainty into the model's learning process, resulting in more robust predictions. Challenges and fixes. Challenge 1: perfect collinearity in features. Sample use case: a model being trained on data containing two features that are perfectly correlated, e.g., weight in kilograms and weight in pounds. Fixes. Feature selection: remove one of the perfectly correlated features. Regularization techniques: use L1 or L2 regularization to penalize large weights and encourage the model to rely on a smaller subset of features. Challenge 2: lack of convergence during optimization. Sample use case: the model's optimization algorithm might fail to converge to a stable solution due to issues like a high learning rate or a poorly initialized model. Fixes. Reduce learning rate: experiment with smaller learning rates to improve convergence stability. Increase number of iterations: allow the optimization algorithm to run for more iterations to reach a more stable solution. Try different optimization algorithms: experiment with different optimization methods, e.g., gradient descent, ADAM, SGD to see if one performs better. Challenge 3. Insufficient data. Sample use case. The model might struggle to learn meaningful patterns with a limited amount of training data, potentially resulting in overfitting or poor generalization. Fixes. Gather more data. The most straightforward solution is to obtain additional training samples. Use a simpler model. Choose a less complex model that requires fewer data points to learn effectively. Employ data augmentation techniques. Synthetically generate new training data by transforming existing samples.